Yes friends, welcome once again to the class. Let us move on towards our question number 1E of physics optional UPSC 2013. The question number 1E, paper 1, 2013 UPSC physics optional. Let us look at the question. Explain why information carrying capacity of an optical fiber can be enhanced by reducing the pulse dispersion. Okay, so what is pulse dispersion? We are going to look at this particular fact, this particular concept of pulse dispersion. We are going to look at it. Okay, and why the information carrying capacity of an optical fiber can be enhanced by the reduction of this particular thing, by the reduction of this particular entity called as pulse dispersion. By the reduction of this pulse dispersion, how we are able to enhance the information carrying capacity of optical fiber. That's what we are going to learn. Okay, and how does one minimize pulse dispersion using a graded index optical fiber? So what is graded index optical fiber? What is step index optical fiber? And how pulse dispersion, how the pulse dispersion is minimized with the help of graded index optical fiber. That's also we are going to learn over here. Okay. Now, in optical fiber communication, you already know that optical fiber communication is there in your UPSC CSE syllabus. So, what is optical fiber communication? In optical fiber communication, this is what the thing which happens is like this. Okay, so the light ray enters the fiber. This is suppose the start of this is the start of the fiber, and this is the end of the fiber. So the light ray enters like this. The light ray enters like this, and then what happens? It undergoes refraction at this particular point. The light ray enters like this, and then it undergoes refraction at this particular point. Okay. Then what happens? Then over here it undergoes total internal reflection. Then over here it undergoes total internal reflection. Then over here, then over here. Okay. So on and so forth. Got it? Now, the thing is that what is this particular term? You already know what is refraction, right? You already know what is refraction. Refraction means bending of the ray either towards the normal or away from the normal. Okay, after the change of medium. So suppose we have one denser medium over here with us. We have one denser medium with us and one rarer medium with us. So when the ray of light will enter the rarer medium from the denser medium, what will happen? Actually, the ray of light will move away from the normal. Okay, let me tell you this particular fact, that suppose this is your surface and suppose this is your normal. Okay, all this stuff you have already learned in the lower classes, but still I am going to brush up the concept so that you understand all of the stuff in a better way. Okay, so what is total internal reflection? That's what we are going to learn over here. Okay, what is total internal reflection? That's what we are going to look now. See, this is ray 1, this is ray 2, this is ray 3. Okay, this is ray 1, this is ray 2, and this is ray 3. Now, what is happening? Suppose a ray of light comes like this, okay, and it goes like this. Then what will happen? So let me mark with the numbers. This is ray number 1, this is ray number 2, this is ray number 3. So we have with us, this is what? This is ray number 2, this is ray number 1, and this is ray number 3. Okay, so this is what? Now this is denser medium, this is denser medium, and this is what? This is rarer medium. What does it mean by rarer medium? The medium which has less density, okay, is called rarer medium. Let me tell you, the medium with less density, it is called as what? It is called as rarer medium. And the medium with more density, what is it called? With more density. Density means mass per unit volume. Okay. So the medium with more density, it is called as denser medium. So what are we looking at? So the thing is that this particular ray number 1 comes like this, and after refraction at which point? After refraction at this particular point. Okay. So after refraction at this particular point, what happens? This ray 1 comes like this and it goes like this. This is ray number 1. This particular ray number 2 comes like this, it goes like this. Okay, this ray number 3 comes like this and it goes like this. So this is all about the rays after moving from the denser medium to the rarer medium. They shift away from normal. Okay. So the rays have successfully shifted away from the normal. Okay. Now there comes a point when the ray will be incident like this. The ray will be incident like this, and the ray will trace this particular path. Okay. The ray will trace the path on the surface. Okay. The path same as the surface. So this is, suppose your ray number 4. This is what? Suppose this is ray number 4. So the ray number 4 is going like this along the surface. Okay. And if you take any angle greater than this, okay, if you take any other angle which is even slightly greater than this, then what will happen? Suppose I take ray number 5. Suppose I take ray number 5. This is what? This is ray number 5, suppose. Okay. Then the ray will move so much away from the normal after refraction. It will undergo refraction, but the refraction is happening at such a greater angle. The ray is bending so much away from the normal. The ray is bending so much away from the normal that the ray number 5 comes like this instead of going inside the rarer medium. The ray number 5 comes out of the ray number 5 comes out of the rarer medium instead of going inside it. Okay, so it is looking like what? It is looking like what? Just have a look at this particular this particular ray. So the ray is coming like this, and the refraction is happening at such a large angle. This particular refracted ray, this is what? This is refracted ray, but this refracted ray has moved so much away from the normal that it is coming out of the rarer medium. It is not going inside the rarer medium. Okay. So in this particular case, we say that total internal reflection has taken place. Okay. What do we say? We say that total internal reflection has taken place. Okay. So hopefully you got the concept brushed up. So the ray number 1 enters like this. It undergoes total internal reflection at this point. It undergoes total internal reflection at this point. It undergoes total internal reflection at this point. Then at this point. Then at this point. Then total internal reflection over here. Okay. And finally it is emerging from the other end. From the other end of the fiber. Okay. So this is how the ray number 1 traveled. So this is what? This is a pulse of light. Okay. This is optical fiber, right? So this ray number 1 is what? It is light pulse. Ray number 1 is actually light pulse. Okay. So in optical fiber communication, the information of signal is coded in the form of discrete light pulses. Discrete light pulses means discrete light rays. Okay, light pulses means light rays. Okay, and it is transmitted through the fiber. So you already saw that how the ray number 1 was being transmitted through the fiber. For the retrieval of information at the detector, now we have one detector over here. Okay, at the other end over here we might have some detector. At this other end, okay, we might have some detector with us, which is detecting the light pulses which are coming out of the optical fiber. So there might be some detector with us at the other end of the fiber. So the information is being carried. Okay, the information is being carried from here. The information inside the fiber is being carried from here up to here. Okay, so the information starts here and the information ends here, and here is the detector which we have with us, which detects the information. Okay, for the retrieval of information at the detector, the pulses should be well resolved in time. Okay, so at the detector at the detector end, that is at the end of the optical fiber, at the detector end, there should be retrieval of information, and for that retrieval of information, the pulses should be well resolved in time. Now let me tell you what happens when a pulse travels. Okay, when a pulse travels along the fiber. Now this is, suppose, your distance. This is what? This is distance along the fiber. And this is, suppose, your ray number 1. This is, let me draw it properly. So suppose we are looking at the rays at 3 particular instances. Suppose the information carrying pulse is like this. Okay, this is what? This is the pulse. This is the light pulse. The nature of light pulse. Now the pulse is traveling along the fiber. This is what? This is distance along the fiber, right? So the pulse will travel again along the fiber. So the pulse now travels up to here. So while traveling, what happened? These were what? These were distinguishable pulses. These were distinguishable pulses. Why these were distinguishable pulses? Because this is independent pulse and this is independent pulse. So we are able to distinguish between the pulses. Now over here the pulses are getting mixed. Okay, the pulses are getting mixed because this particular distinction point is getting blurred. So the distinction point is getting blurred a little bit. So what happened? Okay, distinguishable. This is what? This is distinguishable pulse but distorted. Okay, it is distinguishable but distorted. And what happens at the third phase? Suppose the rays further move along this particular line and the rays now reach over here. Okay, so while moving along the fiber, the rays have reached over here. Now the line which separates these two pulses, the point which separates these two pulses, it was a little bit blurred over here. Now it is completely blurred. Now what? Now it is completely blurred. So what happened now? As it is completely blurred, so what happened? So they have become actually indistinguishable. They have become what? Indistinguishable. Okay, so these two pulses now they have mixed with each other. So they have become indistinguishable. So we cannot, if someone looks at this particular thing, if someone looks at this, he will say that this is probably one pulse itself. He or she will say that this is what? This is probably one pulse itself, one pulse in itself. But in reality, they were two pulses. They were two pulses, but they were reduced to they were mixed to such an extent. The information got distorted to such an extent that now the pulses are appearing as one. Okay, the pulses are now appearing as single pulse. So these are what? Indistinguishable. That is, we cannot tell the difference between the pulses. So they have become indistinguishable, and this is what? This is what is the meaning? Highly distorted. Okay. This is what? Highly distorted. Okay. So hopefully you got the meaning. Now, the pulses should be well resolved in time. For the retrieval of information at the detector, the pulses should be well resolved in time. Now just have a look. Here the pulses are what? These are well resolved pulses. Okay, well resolved. And what about here? Not much well resolved. And what about here? Okay, not at all well resolved. Not at all well resolved. Okay, now we have one detector over here. Suppose we have one detector at this particular point. Okay, so we have a detector over here. So what will happen? This particular pulse, the detector will not be able to detect the information from this pulse properly. Okay, this particular detector, it will not be able to detect the information from this pulse properly. Okay, this particular pulse I am talking about. So it will not be this particular your retrieval system which is kept over here, detector. It will not be able to retrieve the information from this properly. So in order to have the information getting detected properly, we must have such pulses, such resolved pulses, well resolved pulses till the end. Okay, so the meaning is such type of pulses should be there till the end without getting modified. Okay, such pulses which were over here, they should be like that only up to the end, well resolved like that only up to the end. Only then the information can be retrieved properly. Okay, for the retrieval of information at the detector, the pulses should be well resolved in time. But there is broadening of pulses. Okay, so this is what is the meaning of broadening of pulses. So the pulse was like this, now it has broadened, the pulse has broadened. There is broadening of pulses and they spread over time interval as different rays. So what happens? They spread over time interval. So they have spread it, right? The pulse was like this, and this pulse is getting spread over the other, and this particular pulse is also getting spreaded over the other, and they have spreaded over each other. These two pulses have spreaded over each other to such an extent that now they are appearing to be one single pulse. Okay, there is broadening of pulses and they spread over time interval as different rays take different times to travel through the fiber. So different rays take different time to travel through the fiber. Now let us understand. Now consider ray number 2 and consider ray number 1. Okay, consider ray number 1 and ray number 2. What do we have with us? This particular cladding. Okay, let me draw it once again so that you guys understand it in a better way. Okay. So we have ray number 2. What do we have? We have ray number 2 with us and we have ray number 1 with us. So this is what? This is ray 2. Let me draw it properly. This is ray 2 and this is what? This is ray 1. Okay. So this ray number 1 enters like this and then it will actually go like this. Okay. By undergoing total internal reflection again and again, by undergoing total internal reflections, it will go like this. Okay. So this ray number 1, this is what? This is ray 1. This is 1, 1, 1, 1, 1, 1, 1, 1, 1. So what happened to this ray 1? The ray 1 underwent multiple total internal reflections. In total internal reflection number 1, number 2, number 3, number 4, number 5. And at this point it is normal refraction. At this point it is normal refraction. At this point it is normal refraction. But at this point, at this point, at this point, at this point, and at this point, it is total internal reflection. Okay. So this is the thing. Now, let us consider these two rays. Now this ray number 2, have a look. This ray number 2, suppose it enters in such a manner that it is parallel to this cladding. This is what? This is your cladding, right? This is cladding. So every optical fiber consists of a cladding, okay, which has less refractive index. Cladding has less refractive index, and there is one core in the middle of every optical fiber which has more refractive index. Okay. So what happened over here? This ray number 2 was incident in such a manner that it was along the normal. Ray number 2 was along the normal. So that particular ray will not change its path. Okay, whenever something enters along the normal. In the refraction in lower classes, you have already learned that whenever this is suppose your normal, and suppose a light ray comes like this, which is along the normal. So the light ray will not change its path. You already know. In refraction, even if the medium is different, this is medium 1 and this is suppose your medium 2, even if the mediums are different, still the ray will travel along a straight path if it is incident along the normal, that is perpendicular to the surface. So similarly, we are making the ray 2 to be incident. We are making ray 2 to be incident on this particular core in such a manner that it is incident along the normal. So it is incident. So it will move straight through this fiber. Ray number 2 will move straight through this fiber. Okay. And what about ray 1? So it is being incident like this. So it will go like this, then it will go like this, and so on and so forth. Now, whenever something travels in straight line, so distance traveled by ray 1 is greater than distance traveled by ray 2. Clearly from this figure, as ray 2 is traveling along the straight line, so obviously ray 2 will cover the minimum distance. Okay. And what about ray 1? Ray 1 will cover a larger distance. Because it is not traveling along a straight line. It is moving along the zigzag path. Ray 1 is moving along zigzag path, so that's why it will travel more distance, and ray 2 will cover less distance because it is following straight path. So there will be time delay. Now there will be time delay. Why? See, all this particular area has a constant refractive index. This is a core, so it has constant refractive index, and we have one cladding also over here. This also has constant refractive index. Okay. This cladding also has a constant refractive index. Now what happens? Just have a look at ray number 1 and 2. Ray number 1 will take a larger time to reach the end of the fiber. Ray 1 will take a larger time to reach along the end of the fiber. It will take a longer time to reach along the end of fiber, and ray number 2 will take lesser time to reach along the end of fiber. Okay. So what happens? Ray 1 longer time to cross fiber, and ray 2 lesser time to cross fiber. Now, so that's why there is a time delay. This creates what? This creates time delay. Okay, as ray 2 takes lesser time to reach, this creates time delay. So 2-second ray will reach first, and ray number 1 will reach later. This is creating time delay. This creates time delay. Now, because of this time delay, there is distortion in the information. Okay, because of time delay, what happens? Because of time delay, information gets distorted. And why the information gets distorted? Because pulses are not well resolved. Pulses are not well resolved. Okay. So, this is the thing which happens. For retrieval of information at the detector, the pulses should be well resolved in time, so the pulses no longer remain well resolved. But there is broadening of pulses, and they spread over time interval as different rays take different times to travel through the fiber. This phenomena is called as dispersion or distortion. So we call this particular phenomena as dispersion or distortion. As you can see over here, it is written. This particular phenomena is called as dispersion or distortion. Okay. By reducing the pulse dispersion, the pulses remain more resolved at the detector. Okay. By reducing pulse dispersion, now I already told you, right? Lesser is the dispersion, more resolved are the pulses at the detector. Okay. Thus reducing the loss of information while traveling through the fiber. I already told you, right? So information loss will be minimum if the pulses are well resolved, and the pulses will be well resolved when pulse dispersion is minimum. Okay, and pulse dispersion will be minimum when the rays, the time delay between the rays is minimum. Pulse dispersion will be minimum when time delay is minimum. Okay. This increases the information carrying capacity. Okay, so reducing the pulse dispersion increases the information carrying capacity of the optical fiber. Got it? So this increases the information carrying capacity of the optical fiber. So just have a look that what was asked to us, whether we have discussed this particular fact or not. Just have a look. Explain why information carrying capacity of an optical fiber can be enhanced by reducing the pulse dispersion. Just have a look. So what was asked to us? Why we can increase the information carrying capacity of optical fiber? By reducing pulse dispersion. So what is the answer? We have already written it in words. We have already written the answer in words. But let me just give you a brief overview of what we have answered. Okay. See. Less time delay between the pulses leads to what? It leads to less distortion. And less distortion leads to what? More resolved pulses. More resolved pulses lead to what? Better retrieval of information. Better retrieval of information leads to what? Better retrieval of information leads to less loss of information. Okay. Better retrieval of information leads to less loss of information. Okay. So better retrieval of information leads to less loss of information. So this is how this distortion is also called as dispersion, by the way. Okay. So this is what is dispersion. You can write to dispersion also. Okay. So less time delay leads to less dispersion leads to more resolved pulses, more resolved pulses leads to better retrieval of information, and better retrieval of information leads to less loss of information. Okay, so question part 1 of the question, okay, one part of the question has been answered successfully. So you can have a look, you can note all this down in your notebook, this particular slide, just note it down in your notebook, this particular slide, just note it down in your notebook, okay, and this particular thing. So successfully what we have done, one part of the question answered up to here. Okay, so one part of the question answered up to here successfully. Now comes the next part of the question from the next slide onwards. So from the next slide onwards we are looking at the next part of the question. And what is the next part of the question? What does the next part of the question say actually? The next part of the question says, how does one minimize pulse dispersion? How does one minimize pulse dispersion using a graded index optical fiber? So how does a person minimize pulse dispersion using a graded index optical fiber? Okay. So what is a graded index optical fiber and what is a step index optical fiber? That's what we are going to look right now. Okay, right now we are going to look at it. What is the step index and what is graded index? So hopefully you have got the meaning of pulse dispersion. Okay. Now let us look at this part number 2, which is marked with blue color. Okay. So let us look. Just let me have some water because my throat is really aching now. Let us move on towards the next part of the question. What does the next part of the question say actually? Let us see. The next part of the question says that how does one minimize pulse dispersion using a graded index optical fiber? So first of all, I am going to tell you the difference between step index optical fiber and graded index optical fiber. So let me tell you the difference between them. So suppose let us first understand what is step index optical fiber. So suppose we have one optical fiber of this type. Okay, we have one optical fiber which looks like this. Okay, I am drawing it very fast so that the video is not unnecessarily very long. Okay, because nowadays the audience retention is reducing to such an extent that I cannot even tell it. Okay, because the average human is nowadays spending less and less time towards complicated things. Okay, entertainment videos are getting very high retention nowadays. So all these things keep happening actually. The average retention nowadays it's only 8 seconds. Okay, do you know this amazing fact? Average retention nowadays, okay, in 2012 the average retention was 12 seconds. Average retention of a human was 12 seconds in 2012, and in 2023 the average retention of a human is only 7.8 seconds. Okay, so this is the average retention of humans. So the average retention has reduced up to such an extent. Okay, so what is this step index fiber? Suppose this has refractive index n1 and suppose this particular thing has refractive index n2. Okay, and this particular thing has refractive index n2. So what happens? The refractive index n1 will be obviously greater than n2. That is quite obvious. Only then total internal reflection will take place. Otherwise total internal reflection will not take place. Okay, if this particular condition is not satisfied, that n1 greater than n2, that is refractive index of core greater than refractive index of cladding, if this particular condition is not satisfied, then total internal reflection will not take place. So that's why n1 must be greater than n2. That's quite obvious. Now suppose this is step index fiber. So what happens in step index fiber? This is step index fiber. So this n1 is equal to constant. In step index fiber, this n1 is constant and this n2 is also constant. Okay, so n2 is also constant and n1 is also constant in step index fiber. Now let us understand what is graded index fiber. Okay, now let us understand what is graded index fiber. See, suppose this is the core which we have with us. Okay, and this is what? This is your cladding. This is what? This is cladding, and we are talking about graded index fiber. Okay, now cladding has refractive index n2 which is constant. Okay, and cladding again has refractive index n2 which is again constant. Okay, but what about core? What about core? See, from here till here, suppose we consider n1 is the refractive index of core, so that is not constant. Okay, not constant. Let me write properly. Not constant is equal to not constant. Okay, so what happens? The refractive index in graded index fiber, the refractive index is maximum here, n1 maximum at the center n1 maximum, and n1 decreases as we move away from center. Okay, so n1 decreases as we move away from center. Again in this direction also n1 decreases as we move away from center. Okay, so as we move away from center, this is what, this is your center. So as we move away from center, the n1 value decreases. Okay, so from center of the, that is axis of the optical fiber, this center is what, this center is actually axis of the optical fiber. This center is axis of the optical fiber. So as we move away from the axis, okay, as we move away from the axis towards the cladding, away from the axis towards the cladding. Okay, cladding is over here, so away from the axis towards the cladding, again away from the axis towards the cladding. Okay, so as we move like that, the refractive index actually decreases. Okay, so the refractive index over here, the refractive index of core over here will be minimum. The refractive index of core, just a second guys. Okay, so the refractive index of core over here will be minimum. The refractive index of core over here will be minimum. The refractive index of core over here will be maximum. So over here refractive index of core minimum, over here refractive index of core minimum, over here refractive index of core maximum. Okay, and what about this particular layer? Intermediate. Okay, intermediate, and over here it is intermediate. Okay, so such is the thing. This is what for cladding. What about cladding? For cladding everything is same. For cladding n2 is equal to constant. Okay, so refractive index of cladding is constant, but for core, okay, this area is called as core, right? This area is called as core. So for core, the refractive index decreases from center towards the end. From center towards the end, the refractive index of the core decreases. From center towards the end, the refractive index of the core decreases. Okay, so that is what is called as graded index fiber. Okay, so let us compare step index fiber and graded index fiber. Let us compare them. Let us compare step index fiber and graded index fiber. So both step index fibers and graded index fibers use the phenomena of total internal reflection. Okay, so both of them use total internal reflection. Now what is total internal reflection? I have already told you. But both step index and graded index, both of them use total internal reflection. Both have a core and a cladding. Okay. The differences between them have been discussed below. The differences between the step index fiber and graded index fiber have been discussed below. So what is the difference between step index fiber and graded index fiber? We are looking at it. So suppose this ray number 1 enters, this is step index suppose. So in step index n1 is equal to constant, n2 is equal to constant. So both of them are constant in step index. So the ray 1 enters like this, it moves like this in a straight line, and ray 2 goes like this. Okay, so ray 1 is zigzag and ray 2 is a straight line in step index. So that is how the, now why there is time delay in step index? In step index there is time delay. Because ray 1 travels large distance, ray number 1 travels large distance, and ray number 2 travels less distance. Okay, so as ray number 2 travels less distance and ray number 1 travels more distance, what happens? Because of that ray number 1 takes a larger time, longer time I would say rather. So ray 1 takes a longer time to reach here, and ray 2 takes a shorter time to reach here. Okay, ray 1 takes a longer time to reach here, and ray 2 takes a shorter time to reach here. So what happens because of that? Because of that there is lot of distortion or dispersion. So dispersion is large in step index fiber. Now let us understand what happens in graded index fiber. So let me tell you what happens in graded index fiber. Okay, so in graded index fiber actually the thing which happens is that the ray enters like this, and the ray does not travel in a straight line. Okay, the ray in graded index fiber does not travel in a straight line. So let me draw it properly. Okay, let me show you. So this is what? This is suppose your graded index fiber. So what happens in graded index fiber? Suppose this is your graded index fiber, and the ray which has entered from here, it will go like this. Instead of moving in a straight line, it will go like this. Okay, now why will it move like this? Let me tell you properly that why it will move like this. Let me tell you. See, I already told you that in graded index fiber, over here the refractive index is maximum. I already told you, right? I have already told you that over here the refractive index is maximum. Then the refractive index over here, it is comparatively lesser. Then the refractive index over here, it is again comparatively lesser, right? So what happens is that the ray, suppose we draw normals over here, we keep on drawing normals over here, normal number 1, normal number 2, normal number 3. Okay, so what will happen? So the ray is moving from, this is what? This is denser part, and this is rarer part. This is again rarer part. Okay, so from the denser part to the rarer part, the ray is moving. So it will keep on, this red colored ray will keep on moving away from the normal. Why will it keep on moving away from the normal? Because over here the refractive index is maximum, then it decreases, then it again decreases. It decreases continuously. It decreases continuously in graded index fiber. So what happens? The red colored ray keeps on moving away from the normal. Okay, so at all these points, the red colored ray keeps on moving away from the normal. Then total internal reflection takes place. Then they keep on moving towards the normal. Okay, then again total internal reflection takes place. Then at all these points again they keep moving away from normal. Then again they keep moving towards the normal. Okay, then away from normal. Then they undergo total internal reflection here, and then they escape. Then after that they escape simply. Then at all these points they will keep moving away from normal. They will undergo total internal reflection. Then at all these points what will happen? They will keep on moving towards the normal. Okay, why towards the normal? Because when we are moving like this, then refractive index is increasing, so we are moving towards the normal. Then again when we move like this here, then what happens? Refractive index decreases. It was increasing here, so they were bending towards the normal, but it is decreasing here, so they are moving again away from normal. Then total internal reflection. Then again what happens? Then again towards the normal, because from rarer to denser we are moving. Okay, then away from normal. So this keeps on happening in graded index fiber. Okay, so let us see. So this is the diagram for step index fiber, and in graded index fiber the ray moves in a parabolic path instead of straight path in graded index, and in step index it moves in a zigzag fashion. So let us see. So figure which was shown over there, it was time delay in step index fiber. So ray 1 in step index fiber travels larger distance as compared to ray 2, so it takes longer time to travel through the fiber. So ray 1 takes a longer time to travel through the optical fiber in step index, thus resulting, and ray 2 takes a lesser time comparatively while traveling through the optical fiber, so thus resulting in time delay. So this results in time delay between ray 1 and ray 2. Okay, and larger dispersion or distortion. So the distortion or dispersion is larger in step index fiber. Okay, distortion or dispersion is larger in step index fiber. Why? Because ray 1 and ray 2 are taking different times to travel. Now there is minimum time delay in graded index fiber. In graded index fiber there is minimum time delay. Why there is minimum time delay in graded index fiber? Let us see. Okay, so let us suppose this is your ray number 1. This is what? This is ray 1 and this is your ray 2. Again in graded index fiber also, this is your ray number 1. This is what? This is ray 1 and this is your ray number 2 in graded index also. So let us see. Ray 1 in graded index fiber travels more distance than ray 2. Okay, so in graded index fiber also ray number 1 travels more distance as compared to ray number 2. Okay, but both of them take the same time to reach the end of the optical fiber. So ray number 1 takes the same time as ray number 2 to reach the end of the optical fiber. Why? We are going to learn now. Okay, but both of them take the same time to reach the end of the optical fiber. This is because as the refractive index N1 of the core is maximum at the axial part. Okay, this is because as the refractive index N1 of the core is maximum at the axial part, means at the center of the optical fiber, at the center of the core, the refractive index of the core is maximum, and the refractive index of the core decreases moving away from the axis. So the refractive index decreases as we move like this. The refractive index decreases. As we move like this, the refractive index of the core decreases. Okay, so what happens? So let us see what happens because of this. Okay, this is because ray 1 takes lesser time to travel near the. So what happens? Your ray number 1 takes lesser time. Ray number 1 takes lesser time to travel over here. Okay, see, over here the refractive index is less. And over here the refractive index is more. So the ray 1 will take more time here, then less time here because refractive index is low over there, less time here because refractive index is low over here, less time here because refractive index is less over here. Okay, and ray number 1 will also take more time over here because refractive index is maximum over there. Okay, so but ray 2 will always take maximum time. Because ray 2 travels in a straight line along the axis. So ray number 2 will always keep taking maximum time. You already know that as the refractive index increases, okay, as the refractive index increases, what happens? As the refractive index increases, the velocity decreases. Okay, velocity of a ray, the velocity of a pulse is inversely proportional to refractive index. More is the refractive index, lesser is the velocity of the ray. So in this ray number 2, as it is moving along the axis and maximum refractive index is there on the axis. Ray 2 is moving along the axis and maximum refractive index is there along the axis. Okay, so the ray 2 will always take maximum time to reach over here, but ray 1, although ray 1 is traveling a larger path, although ray number 1 is traveling a larger path, but over here it is moving faster because refractive index is less. Over here it is moving faster because refractive index is less. Over here it is moving faster because refractive index is less. Okay, so even after traveling a larger distance, okay, velocity is more even after traveling larger distance. So what happens is that less velocity and less distance. Okay, time is equal to what? Time is equal to distance upon speed. Okay, distance upon speed is equal to time. Now when speed is less, suppose speed of ray 2 has lesser speed, right? Ray 2 has lesser speed, so ray 2 has lesser speed, so distance also it is covering less because it is traveling in straight line. On the other hand, for ray 1, what happens? For ray 1 the velocity is more because it is going towards the cladding. Okay, so for ray 2 the speed is more. For ray 2 the speed is more. Okay, for ray 1, sorry, not ray 2, for ray 1, speed is more. Okay, speed is more, but distance is also more. Okay, so what happens? Time taken by both of them, so the result is that time taken is same for ray 1 and ray 2. For ray 1 and ray 2 time taken is same because of this particular fact. Although ray 1 is traveling more distance, but it is going through here also, so at those points refractive index is less, so it will travel faster at these points, so it will be a total overall compensation. Ray 1 takes lesser time to travel near the cladding. Okay, so ray 1, let us see, ray 1 takes lesser time to travel near the cladding. Okay, this is what has been described in the words. Ray 1 takes lesser time to travel near the cladding due to increase in velocity because of decrease in refractive index near the cladding. So near the cladding refractive index decreases, so velocity increases. So as velocity is inversely proportional to refractive index, and more is the velocity, less is the time required. Thus time delay is minimum, and so is the dispersion. So that's why the time delay is minimum and so is the dispersion, because ray 1 and ray 2 in graded index. What happened in graded index? Have a look once again. Okay, I am explaining it once again just for you. In graded index, what happened? In graded index, what happened? In graded index, suppose this is ray number 2, this is ray 2 which is traveling like this. Okay, this is ray number 2, and I am marking with yellow color. This is your ray number 1 which is traveling. So this ray 1 went like this, and then after that the ray 1 is traveling like this. So what happens in all this process? In all this process, the refractive index is maximum here. Okay, refractive index is maximum here, and the refractive index is minimum over here. The refractive index is minimum. Over here the refractive index is minimum. Okay, so because of that, have a look at this particular yellow ray 1. So it was moving slow, then it moved faster because of less refractive index, then again it moved slow because of more refractive index, then again it moved fast because of less refractive index, then again it moved slow because of more refractive index, then again it moved fast because of less refractive index, then again it moved slow because of more refractive index, then again it moved fast because of less refractive index, then again it moved slow because of more refractive index. Okay, so less velocity, more velocity, less velocity, more velocity, less velocity, more velocity, less velocity, more velocity, less velocity, more velocity. Okay, and what about ray 2? Ray 2 always less velocity, because moving toward along the axis. So ray 2 always less velocity. So always less velocity person is traveling less distance. Okay, and a person whose velocity is accelerating here, velocity is accelerating. So that person, even if he travels more distance, okay, even if that ray 1 travels more distance, still it is going to take the same time to reach here. Why? Because the velocity is fluctuating, it is increasing also sometimes. Okay, so in more velocity, if you have more velocity and you are traveling large distance, more velocity in large distance, so ultimately the combination is such that ray 1 and ray 2 reach the same time over here. So what happens then? In graded index fiber, as ray 1 and ray 2 take same time to reach, in graded index ray 1 and ray 2 take same time to reach the end. So what happens because of that? because of that less distortion, okay. So less distortion means less loss, less distortion. And why was it less distortion? Because of less time delay, okay, because of no time delay, actually no time delay. So because of that less distortion, right, because of that less distortion, and because of less distortion less loss of information in graded index, So hopefully you got the thing, okay. So in this way you can write the answer to this particular. You can stop the screen and note down the answers. So successfully we have successfully solved question 1E 2013 physics optional paper 1, okay. Question 1E solved successfully. Thank you very much.